It's hosted by the VCCN in the Netherlands. And we have as a theme of this webinar, product cleanliness. And we have a couple of interesting topics that we would like to present. And the first presentation is about the future contamination control 2050. It's an outlook and it's an in-depth evaluation of the future that's ahead. And it's presented by Erik Stuyver from Deerns Consultancy and Design. Erik is also a current VCCN chairman, and it's also presented by Christopher Perry. He's from Vakwerk Architects. Erik has 35 years of experience in cleanroom design. Christopher has more than 15 years experience, and we'll be very pleased to allow them to give their presentation.
Thank you very much, Frans, for your kind introduction. Also, together with Chris, we will take up, let's say, the challenge to take you to the future. I also see myself now, that's good. Actually, we have prepared, I will try to switch to the next slide. I think, sorry for the interruption. Jos, kun jij? Ja. Hij deed het wel, maar nu niet. Ja, please. As technical people, we are always struggling with the technique, so no. It's not. Okay. Did you press? That's also fine. Yeah.
Okay.
Yeah. Okay. Okay. If we asked our technical supervisor to take over the slide handage, so please, can I have the next slide, Jos? No. Yeah.
Here we go.
That's it. Goes very good. Good. Now, Frans gave already a short introduction. Maybe I just can add to the point that I'm basically already 35 of years experience, different kind of experience in clean rooms and contamination control. Actually, I started at Philips, actually my first experience with clean rooms. And ever since that moment, I have been involved and currently also in the design of clean rooms, not only in the Netherlands, but also on a global level together for the company I work for, Deerns, at the moment. So maybe it's good also, Chris, if you can.
Sure. My name is Chris Perry. I'm an architect by background, and my experience has been in the design, construction, initially of microelectronic manufacturing clean rooms in the States, Taiwan, Europe, and increasingly over the last few years, I've been working on the design of research facilities for nano, micro devices.
Perfect. So together we have more than 50 years of experience, but the challenge is not to share that experience with you, but try to look, let's say, beyond our current shadow, so to say. So what we would like to do in the coming minutes with you is to take you a little bit back to where we are, the world behind contamination control and why contamination control is so very important. Then we will take a look at what is happening in science and technology, because you can imagine that that is the precursor for what is going to happen in the next decades. And then Chris will take a closer look at what does it mean for clean rooms and facilities. So what is the impact on that? And then in the second part, we will look a little bit more about the value chain. And of course, when you think about value, you think about money. But I will not, let's say, spend already words about that. But there is more to value than just, let's say, from a money point of view. And then, of course, we will summarize and give you an outlook as a sort of overall picture. Chris, maybe you can start first explaining why contamination control is so very important.
Yes, of course. Contamination control, I suppose the starting point of this has been clean rooms, where the control of particles has been an essential part of the process for advanced manufacturing. But increasingly, as the science has evolved and the geometries have reduced and the scope of the science has increased, then other contaminants have become increasingly important to be able to control for the manufacturing process. So while we started with particles, now issues such as vibration, electromagnetic interference have become increasingly significant. And then at the same time, I think one of the interesting things we're going to sort of discuss then is how the engineering or the discipline has become more interdisciplinary, where life sciences and microelectronics, nano, quantum are beginning to overlap. And then I think you see this evolution in technology, in the value of this industry, which has, if anything, flourished during the last 2 years of COVID, as vaccines have been developed and tested and distributed in incredibly short periods.
Okay, as we said, basically, if we try to look what's ahead, then of course the baseline for key developments, especially in the high-tech world, is about science and technology. So what we have tried to do here is to give, let's say, a sort of overview of what is happening there. And then basically, of course, from the key sectors that you can identify with respect to contamination control, being electronics, and of course also life sciences. And if you look at, let's say, the long-term trend there, then basically you can see some interesting trends there, because what you see in electronics, everything is becoming smaller. Nowadays we are talking about nanometers. But you can see more or less the opposite is happening in life sciences. There things become larger because scientists are able to construct basically larger molecules with more functionality. So these are, let's say, long-term trends that are already taking place for the last decades. And I think they also will continue. But now the interesting thing is that we are on a crossroad, more or less, that these two come together. And when people meet, also new things can develop, and that is actually also what you see. So for instance, you see now materials coming up like bioelectronics, molecular switches instead of electronic switches, and even a lab on a chip is now also part of the market. And the question is, of course, how will that continue? This gives you a little bit of a snapshot what especially scientists are working on in different type of sectors. For instance, in the food sector, sustainability is becoming a very crucial issue, and there also contamination control, as we know it, will become more and more important to make that happen. But also when you look at our devices and chips nowadays, there also will take quite some big changes. For instance, we are now using electrons for switches, but you can do that also with light. So photonics is there. And as Chris already mentioned, quantum technology is also becoming part of, let's say, not only science, but also more and more applications. So if you even follow the news a little bit, these are just some examples what we think, and we have also discussed with our clients that this will happen in the next 10 years probably. So first of all, you see, for instance, the upcoming quantum technology. And that is not only from a university, but also big players like Microsoft and Intel are picking up that development now. But also when you look at miniaturization, we're talking now about nanometers, but for instance, an institute like IMEC, together with ASML, is already working on devices below 1 nanometer. So also their developments will continue. And also, just as an example, if you look at the energy transition that is going to take place or is taking place, there also scientists are working together on new technologies to produce, for instance, by the fusion technology, with ITER in France is an example. So a lot of things are, let's say, beyond already the drawing table, so to say.
So to put those geometries into perspective, I think this is a diagram you'll be familiar with, which shows the relative size of animal or plant cells over on the right, down to molecules and atoms down on the left-hand side. And the kind of the key item within a clean room, the HEPA or ULPA filter, originally designed to be effective at 0.3 of a micron. But now that the geometry is reducing, it's under review as to what its effectiveness is. And I think the latest research is showing that it's capable of filtering down to about 10 nanometers, which does raise the issue about how can nano-engineered particles be controlled once that level of geometry has been found. But the devices which are allow your laptop or phone to work are now being manufactured with critical line widths of between 5 and 10 nanometers.
Now here's also the question, of course, will, let's say, this trend continue towards smaller particles? As we have seen, smaller dimensions are possible. And what would it mean for control of particles? Because that is, of course, as VCCN, also as ISCC, as our key focus area. And we do expect that particle sizes is not, let's say, on a certain limit at this moment. Certainly it will shift farther to the left, meaning smaller particles. Meaning control levels have to be, let's say, increased. When you only think about something like a single electron transistor, that is something that has to be controlled in order to make it function. That means the environment has to be controlled on an almost single electron level. And that are some challenges, of course, that are ahead of us. If you try to summarize a little bit where we are and where we are going to, and try to make it a little bit more practical also for you as an audience, that basically you see that things are becoming smaller. That means new products and applications can be developed and also be transferred into products. But it also means that the criticality and diversity of contaminants is increasing. And the number of parameters you see here is not only about particles, not about bacteria, but it's also about vibration control. And Chris, I think you can give some daily practice examples also on that.
Yes, I mean, the way now that critical tools are analyzed is looking at a whole range of factors through temperature, humidity, EMI, vibration, sound pressure, noise levels, and in the case of quantum engineering, then being able to achieve pretty well absolute zero temperature to give stability or lack of movement at the molecular level. So the definition of contamination keeps changing as different criteria are critical to the equipment needed for manufacturing.
And of course, then the question becomes also more practical. What does it mean for clean rooms? What does it mean for the clean room in itself, but also for the facility which basically makes the clean room? Also there, when you look at, let's say, the long-term trend, basically you can see also there a certain direction where we are going. In the early days of the clean room, basically it was a ballroom, a bigger area with a certain classification. And the direction is to go smaller. That means also the critical area within that clean room is becoming smaller and smaller. Via a tunnel concept, mini environment concept, and even clean machines where the environment is in the production or research machine itself. And the last days, or the last 2 decades, basically we see from the nanotechnology that you cannot, let's say, start with one clean room that takes care of everything. You have to split it up in different entities to make sure that what Chris already explained about vibration control is can be controlled only local level for certain technologies. And that is now what you see, but you see it also in the bio-nano combination, where you also have what we traditionally call pharmaceutical clean rooms combined with electronics clean rooms. And we think, if you look ahead, that trend will continue. So you will see in a clean room facility more functionalities with different specifications, but also introduction of let's say, new applications like automation, but also new technologies like EUV to make things even more smaller, which also does require some environmental aspects to control in a better way. But also quantum technology is taking place into the clean rooms in order to make it a production level. If we try to summarize basically 4 key trends there, so we see continuation of the reduction of critical area in the clean room itself. Try to people move out as much as possible to minimize the interference there, helped by automation and robotics, of course. And what we also need, and Chris will explain it later in a few examples, also smart adaptive control. And last but not least, these are all technical aspects, but there is, of course, something beyond the technical aspects as well, and that is about sustainability. And we will mention that topic also later in our presentation. But first, some examples on the facility impact in more detail.
Great, thanks, Eric. So what you see here are just 4 illustrations or 5 illustrations of different cleanroom types. So starting on the top left, the positively pressurized, probably an ISO 3 or 4 cleanroom, very tight controls on temperature and humidity. On the right, a pharmaceutical cleanroom, negatively pressurized, concerned to protect the users as against the product, and with a glove box there, so containment within containment, given the risk from potent drugs. Bottom left, a biotech type clean room, probably a biosafety cabinet in there, which would protect both the user and the thing the organism being studied. And then on the bottom right, a clean room for critical manufacturing for space vehicle, and then which would be a positively pressurized clean room where the product is being protected. And then there's now the evolving market, which is somewhere between critical manufacturing and microelectronics for quantum research and manufacturing, less critical for particles, but certainly critical for vibration and to support work at extremely low temperatures. But what brings all these things together is these are supporting the markets for data, communication, and health. Very dynamic markets with an expectation of innovation and ability to bring new products to market incredibly quickly. So looking at some novel products and products which span different disciplines. On the left-hand side, you see a little piece of etched glass which forms a gas chromatography chip with the wrapped column on the left-hand side and the connections for the carrier gas and the sample gas coming into it on those tubes on the right. The illustration on the right then showing a tiny scale drug application chip made with a combination of novel new manufacturing techniques, plastic printing for that little mixing valve in the center of the object, and then a emboss printed polymer or soft silicon holding it all together and creating the channels through which the chemicals are distributed. This is a project for Southampton University, something I spent a couple of years working on, which has a range of different clean rooms put together within the same facility. So optical fiber clean room on top left, possibly pressurized, hazards to do with contamination from the fibers that are being created within it. A small novel electronics clean room. And then in the middle of it, the green area is a biosafety level 2 clean room, capable of being upgraded to 3, but for the manufacture or the development of lab on chip biochips. And then the big clean room at the bottom, a microelectronics type clean room, and then finally characterization lab featured at the front of the space, from which anything that was produced there could be analyzed and understood. So within the facility overall, here we go. Yeah. What you can see there is the clean room on the ground floor, labs, primarily laser labs above that, and then office space on the two top floors of the building and the utility building on the left. But the illustrations then show how this facility allows different disciplines to create, invent, research, and then make micro devices, and then analyze to see what they've made. So one of the kind of interesting developments in manufacturing and to a degree research then is the increasing automation of the processes, and obviously what's supporting that then is the drop in the cost of the robotics. So repetitive tasks can be taken care of by what you see on the left, a cobot, a collaborative robot, just loading, unloading, sorting samples. But then on the right-hand side, the process of the transfer of the product, in this case, human samples for genome sampling, is handed over from equipment to equipment in a clean room designed for humans to go in there for maintenance rather than for operation. And obviously, as it's a genome facility, it's very sensitive to contamination. The contamination, therefore, being largely removed by people simply not being present. And then kind of returning to that theme about speed to market and the need for fast evolution of products. This is a laboratory for Eli Lilly, which is a research and development sample lab, which is remotely operated and completely robotic. So a series of linked work cells which allow new novel compounds to be made, from researchers working remotely from this facility in California. So there are almost two different themes there you can see from these research facilities. One where everything is brought together, different disciplines and different clean room types brought together. But here, this is a remote facility, but is accessed by researchers in different places around the world. So energy efficiency, clearly in a building, in a facility where you have multiple air changes per minute and you have huge exhaust rates, then the energy consumption is significant. So the importance of driving down energy use has become more critical over the last few years. And the techniques which have been used to address that, then a lot of which are common sense, to do with reducing the critical areas, to reclaiming heat, to using less energy intensive forms of humidification, other than being able to drop the temperature of the air. Are developed at the same time as better automation and controls. So on the next slide, then this is a chart which links the presence of people within a clean room, being the yellow stepped part of the chart, with the particle count. So obviously, if you can then link your controls for air change rate back to the particle count in this space, then you have the ability to drop your energy use according to the state of use of the clean room, which again overlaps with the issue about removing people from the clean room. Safety. So, I mean, the clean rooms will have multiple methods of ensuring reliability and safety, from different power supplies, reliability on the power supplies, redundancy on the power supplies, and through to the detection of toxic materials, of smoke, fire, But these are all primarily aimed at people rather than the product. So the criticality of these kind of reduces as the number of as people are removed from a clean room.
Okay. Of course, these are some examples which are basically currently taking place, the focus on there. So what we have tried to do up to now is give you an insight about, okay, what is happening in the contamination world and what will probably have the key impacts on the facilities as we know them nowadays. And I already explained that we also want to take a little bit of different view, not only on the technical part, but of course also on the financial, the market impact, and also on another aspect. So let us first look at the global market. As we see, as a key application, clean room facilities, contamination control is crucial for basically three key market sectors you can identify. First of all, for research and development. That's basically where it starts and where a lot of things are happening. The same applies for life sciences and of course also for microelectronics. But if you take a snapshot of where we are and also what are the projections not only from governments but also from commercial institutes, basically you see everywhere double growth taking place at this moment. And of course maybe this is a peak that we now observe because of several reasons. But if you also look, let's say, what the possibilities are that are basically available and will become available, then you can expect that this growth will continue at least for coming decades. So that's good news. And on the other hand, you see also some restructuring in the overall structure of, let's say, the contamination control. You see, for instance, especially Europe is not only looking at research and development, but is also looking more and more towards production. Because, and Chris explained that also, production is not building, let's say, a factory and put equipment in and that's it, and then you have a product. No, it's really about full integration with robotics, automation, so it becomes all very smart, hopefully. So that means also the high tech is not only research development, but also more and more focused on the actual production of it. So that is definitely something we will see more in the future. And then, of course, we have been, Chris and I have been looking at what we see as trends. And there is one thing we should not forget. This, let's say, this miniaturization, making things smaller, makes facilities larger, bigger, but it also comes at an energy price. Just these are some examples from the electronics industry. Basically what you see when you go from certain dimensions, in this case about 30 nanometers, and you go to as low as a few nanometers, you see basically a factor of 3 increase in energy requirement for, let's say, a certain product. And you basically, of course, you see this, the same for indication for the CO2. And that is, of course, something we don't want. And before we go into the consequences, maybe, Chris, you can also highlight another aspect on that.
Well, one of the issues then is as geometries reduce, the ability to contain pollution becomes harder. So whether I think a nanoparticle is defined as an object which has a geometry of one dimension of less than 100 nanometers, and these are just very difficult to control. So we live in a world where it seems that we're all carrying a certain amount of microplastics, which are relatively easy to identify. But nanoparticles then is a risk. There is no set method of dealing with them yet. Generally, it's dealt with on a risk basis for the different processes. So there's a heightened, I think, awareness in the environment that we need to be clear about this to address people's worries, concerns about contamination. And at the same time, we're living in a world which has just got used to everybody wearing a mask for the last 2 years, and wearing a form of filter. And then there was this new product which shows that maybe people are going to get used to wearing their own air filtration system to walk around to deal with contamination.
Now, what will happen basically if you bring all these factors together? Because we talked about energy, but of course, I think you mentioned also already, you talk about gases, you talk about chemicals, you talk about exhaust systems. So basically all these factors are part of the clean room facilities. So if I try to translate it to what will be the future about, let's say, about clean rooms, contamination control, you have to look not only at the contamination as we know it nowadays, but you also have to look at the environmental issues, which can be also identified, as Chris explained, as contamination, but it is really part of the facility, inside or outside, and also, of course, the energy that you require. So an integral approach is becoming basically a necessity to make, let's say, the long-term developments feasible. Before we go to our outlook as such, maybe it's good to shortly summarize what we have tried to explain to you and also to present to you. Of course, the first thing about technology, the continuation in miniaturization. We think that we are already working on small levels, but it will become more and more smaller in the near future as well. High tech is increasingly relying on contamination control. The traditional sectors, as we know them, there will become more sectors on board to make contamination control one of their critical aspects in their research or in their production. And contaminants diversify, and they become also more strict. So that's also definitely a technical challenge there.
And then what you will see then is the increased use of automation and robotics within these facilities, partly as a result of the need to speed and remove the human load on activities, but partly as a way of addressing safety and contamination control. Then I think, as we're just describing there, that the concern for the environment only gets greater and greater, and I think we're discovering that the state of the world seems to be worse than we had imagined, and industry is a way of both dealing with that contamination. So it offers a solution to how we can control contamination, while at the same time being a risk to the environment.
So then, of course, the question is, how can we do that? And I think basically what we try to identify, that you can only do it interdisciplinary, not only expert on contamination control, but also environmental control, architects, etc., etc. So we can only do it together. And that's maybe also a good, let's say, starting point for this webinar. Basically, we are trying to make a better world, and we can only do it together. So let's say that is ready to be, to be ready for the future. That is our key message here. And when you talk about a product, there's always a disclaimer. So we have been trying to give you insights what could happen, but of course we also know that technology, they go and they grow exponential. They change faster than we usually are prepared for as human. So we always have to be prepared for the unknown. So we would like to thank you for your attention, and maybe Frans, you can take over the floor.
Yes, thank you very much, Eric
and
Christopher, for your interesting outlook. I think the message is clear that we have to look ahead all together, and that totally coincides with the aims of the ISCC', uniting all the contamination control societies worldwide in the effort to perform best and to deal with the challenges that are nowadays and also ahead. So once again, thank you very much. The next presentation will be on another side of the scope of our subject on product cleanliness. The presentation is given by Freek Molkenboer, a senior systems engineer at TNO Technical Institute in the Netherlands. And he is working mostly on high complex systems involving vacuum or contamination control related issues. Freek will talk about ultra clean vacuum, the right level at the right location. And I really like to give him the possibility to give his presentation, which is pre-recorded, so you know why he is not present in this studio, but nevertheless he is able to provide his presentation. And let's start.
Go. Good afternoon. My name is Freek and I work for TNO, that's a Dutch independent research organization. I work in the department Nano Instrumentation that mainly works for the semiconductor industry and is specialized in contamination control and with that also in ultra clean vacuum. That is also the name of my presentation, ultra clean vacuum, the right level at the right location. This is the outline of my talk. I will discuss why ultra clean vacuum is needed. I will do that by two examples, EUV and TEM. And after that, I will discuss a method how you can prevent contamination, and I will end with a conclusion. So let's discuss EUV lithography. There is a drive for smaller and smaller chips. ASML, that's a Dutch company, made an EUV machine. And that is radically new compared to the older machines. It goes from laser light down to 30.5 nanometers. It is done in ultra clean vacuum and it moves from lenses to mirrors. It has to go to ultra clean vacuum because EUV with the 13.5 nanometer is absorbed by nearly everything, including air. So let me explain vacuum. If you look at Wikipedia, vacuum is a space devoid of matter and at zero pressure. However, zero pressure and zero matter is not achievable. If you look at the best man-made vacuum, that's 10 minus 12 millibar, it still contains 10 to the 5th molecules per cubic centimeter. So still a lot of molecules. And a nice number to know is that at the pressure of 10 minus 6, you still have one monolayer of growth, contamination growth, per second. Vacuum has many applications. I would say it's a big enabler for the current high-tech industry. For example, if you have a look at CERN and on the moon, there we have the 10 minus 12 millibar. SEM, that's also high vacuum, 10 minus 9. And more commonly, we have fluorescent light, the light we have in your room, that's at 10 minus 4 millibar. So many applications require vacuum, and many applications require ultra clean vacuum. This is an example of carbon contamination in EUV lithography. How does it work? In vacuum, there are a lot of molecules flying around. Some are called hydrocarbons. These hydrocarbons flow around in the vacuum vessel and land on, for example, mirrors. At the moment, the molecules are on the mirrors, and the EUV photon hits the molecules, and the hydrocarbon is separated in hydrogen and in carbon. And that leaves a residue on the mirror. Here you can see an example of a mirror on Sematech, and here you can see an example of an off-table mirror in 2007. This is a known issue, and in this case ASML has been working on this very hard, and I think they have achieved to reach an ultra-clean vacuum system. This is more a graphical picture of what I just described. So we have molecules flying around in the vacuum system, and this picture shows the molecules growing on the surface. At this moment, the EUV light hit the molecules, and you can see the carbon has grown on the mirror. If you continue doing this, you get a big layer of contamination growth, and that will reduce reflectivity. Another example, as promised, is TEM. TEM is used to show very small structures. I've chosen to select a TEM image of the coronavirus. We all have a lot of issues with corona, so that's, I think, it's very nice to show that it is possible with a TEM to measure how the virus looks like. In a dedicated experiment done by Thermo Fisher, is that if you load samples that are filled very dirty, so with hydrocarbons, you can show a carbon spot growing on your sample, but also if you have a sample that has too much water on the surface, it will also grow ice. Both are negative for the TEM, but both also are negative for your sample. So with this I've shown you two examples of why ultra-clean vacuum is needed. And now I will move forward explaining how you can hopefully reduce the risk that you have a contaminated system. I will do this by the example of EBL2. EBL2 is a large research facility at TNO that we use for EV-related contamination research. We are able to load samples, but also EV reticles, into the system and expose those samples to EV radiation. This system has to be ultra-clean vacuum system, and it also has to be particle-free. It is not completely particle-free because that's not possible, but we try to reduce the amount of particles as much as possible. So, how do we prevent or limit contamination as much as possible? We do this by a system approach. And this is a very common used method within system engineering. It's called the V model. So for contamination control, you have to add a contamination budget. And it's very important that you discuss what kind of cleanliness level you need at a certain location. I will give that example to you with EBL2. As promised, I will do that with describing the sample route and the required vacuum levels at each vacuum chamber in EBL2. So this is the top view of EBL2. On the left side we have the EUV source that generates the EUV light. Then we have the collector module that will transport the light from the EUV source to the exposure chamber, and in this exposure chamber the sample is located. There are several other chambers on EBL2. We have the XPS, that's a measurement tool to measure what is happening on the top layers of a sample. We have the vacuum handler, that's a vacuum vessel with a robot inside that moves the sample from one to the other chamber. We have a parking cleaning chamber, and we have, importantly, a load lock. And we have an atmospheric handler. Let's go to the atmospheric handler after this slide. This is the example of a sample we have, and we expose in EBL2 on the sample holder. So it's 1-inch samples that are mounted on the sample holder, and after that the sample holder is loaded in an outer pot. That's an ISO standard within the semiconductor industry for loading samples. So this outer pot is loaded onto the atmospheric handler. This is the side image of the atmospheric handler, and what we have done, we have separated the atmospheric handler in two sections, an ISO 4 section and an ISO 1 section. That enables us to have an ISO 8 clean room for the people to operate. So we have several sections to get particle-free, particle-less samples into the EBL1 system, EBL2 system. After loading it in the atmospheric handler, it is placed inside the load lock, and the load lock will evacuate from atmospheric to vacuum pressure. So this is the load lock that will evacuate from atmospheric to vacuum, and after that it will be transported to the vacuum handler. And I repeat myself, that will load the sample from towards each chamber that is desired. And the last chamber I will discuss is the exposure chamber. The exposure chamber is the cleanest chamber in our system because in this chamber the experiments take place. So, as promised, let's look at the vacuum levels. Again, the names of the vacuum vessel. So we have storage, float lock, park and clean, vacuum handler, and exposure chamber. Now I plot the expected or desired end pressures of the vacuum chambers on the chambers. So if you look at the load lock, there I state the end pressure should be better than 10 minus 6 millibar, also stated here. And for the exposure chamber, we state it should be better than 2 times 10 minus 10. That has to do that you can expect that the sample will be in the load lock very briefly. You load a sample and then you will transport it immediately to the chamber that you desire. So that's why we say, okay, 10 minus 6 is okay, but in the chamber where you do the experiments, it will stay longer there, so the pressure has to be way better. 4 times better. Also, if you look at the partial pressures, so that is the molecules that are inside the vacuum, you can see for the load lock, it's not that strict, 10 minus 10 and 10 minus 10, but if you look at the exposure chamber, all should be better, so the combined gases should be below 10 minus 12. So big difference. This big difference means also that you have to do way more pumping, cleaning to reach these pressures. So that's why you have to think about what vacuum level you need at what chamber. So I already pointed towards it. We have to discuss manufacturing. When you think about the design, you must select materials that can resist chemical wet cleaning. It must be also resistant against higher temperatures. A bake-out, a cleaning, normally is hotter than 100 degrees centigrade. That means that most plastics are not be able to use anymore. And you must make sure that in your design you have all surfaces are reachable. If you have surfaces that mate, you cannot clean there. So that will give contamination. So you have to think about that in design. The machining equipment must also be clean, and you must use the correct lubrication and correct cooling fluids. If you select a cooling fluid that is not being able to be cleaned, you have a problem. So you have to think about that. And you should not use tools that are used for non-clean parts, because you will contaminate the product you are making with those tools. And finally, you make sure that the people who assemble the product know that it must stay clean, and therefore you need to give clear instructions how they should do the assembly. So, as I discussed, the exposure chamber is the cleanest chamber in EBL2. We need to handle samples inside the exposure chamber. So we had to think of a solution. There are strong limitations on the allowed materials that are able to be used in EBL2 exposure chamber, and all the parts need to be able to clean. Here you can see a picture of what we call the sample chuck. It is the sample chuck with which we load the samples, and this is the other side of the sample chuck. From this side, the UV light radiates the sample. If we zoom into more detail, this is the gripper that will grip the sample. And I'm afraid it's not very good visible, but on this side there is a special dedicated piece of metal that touches the sample holder. What we do is also we do not use any electric power inside the exposure chamber. We do this motion with pneumatics. So by actuating a spring inside, we move around the gripping part. And in the end, you see a lot of springs, and again this bellow, and here is the gripper again. So a very complex design because of its ultra high and ultra clean vacuum. If this was not in ultra clean vacuum, the design could be way easier. But a lot of limitations, cleaning, ultra clean vacuum, resorted us to make this design. So after manufacturing, of course you have to do the cleaning. This is a picture of our cleaning street at TNO. So we do wet chemical cleaning. And what is important is that before you enter these 6 cleaning baths, you do a very good and proper manual cleaning of the parts. As you can see, the operator is cleaning every part of the holes, the tap drills, to make sure that the cleaning baths are not contaminated. After cleaning, the parts are placed inside a vacuum oven and baked out for prolonged time to make sure all the water is removed and all the trace hydrocarbons are also removed. So, then we have discussed validation, checking that something is clean, and it is done with an outgas measurement. So this is a setup at TNO. It consists out of a vacuum chamber with a pumping set and an RGA, residual gas analyzer. An RGA is able to measure all masses that are present inside a vacuum system. So we have a sample. This is the example I use, and you can expect when you enter it into vacuum that molecules will be pumped away, pumped off the surface. So when you do that and you use the RGA, you can measure the masses that come off the sample. So this is a picture of an RGA scan, starting at mass 0 going up to mass 200, with also included the outcome of this report. So we are looking at total outgassing, we are looking at outgassing from 45 up to 100, and 100 up to 200 AMI. Those are the commonly used values within vacuum engineering to check is a product clean or not. So let's discuss VCCN guideline number 12. So this guideline was released last October 2021. It was a joint effort by OEMers and suppliers, and what we did is we moved from internal company standards, we moved to ISO standards. That's very important to go to ISO and align all cleaning methods and thinking about contamination. So you can see again the V model, and I think we have a nice overlap of thinking about how clean should something be and about design, and a lot of chapters about how you should do the manufacturing, producing and assembly of parts, and we also think nicely about how do you do your testing if parts are clean or not. So in conclusion, I think the need for cleaner and cleaner products will increase in the near future. To control cost, understanding the impact of a cleanliness requirement is needed both for the end user and for the supplier. If you want to say, oh, everything needs to be 100% clean, it's going to be very expensive. Thinking about, oh, is a little bit less clean possible, is something you should do to save cost. And discussing this, understanding should result in the right level at the right location. And that is the end of my presentation. I want to thank you for your time.
Going deep into vacuum and deep into machines. Now we step over to the third presentation, and just in between I'd like to remind you that when you have questions you can put them in the chat, and we have, after the next session, we have the possibility to get some interaction with the speakers that are available here, maybe to answer your questions. Going deep into vacuum and deep into machines. Now we step over to... Okay, the next speaker is Koos Agricola. Koos is active within the field of contamination control since 1986, where he discovered that for the control of fatal contamination, particle contamination, it's very important more to look at particle deposition than to look at classification in air. And he has done a lot of work in his previous job on, I would say, Canon production and printing. But also involved in developing equipment for particle deposition measurement at Brokerhuis Applied Data Intelligence. He has been active within VCCN, within NEN, within ISO on writing standards and developing standards, how to deal with that. And yeah, I'm really happy that he has found the opportunity to talk with us about particle deposition rate, because that's a key to contamination control. And I'd rather like to give him the floor. Koos, be welcome.
Thank you very much for your introduction. After the first presentation of Chris and Eric, where we were looking in the future and we were looking at the left spectrum of particle sizes, nano-sized particles, and then Freek talking about molecular contamination, even further left to the scale of particle size, I'm going to look at the other side. I'm going to look at contamination by macroparticles. In all clean rooms where people are working, there is a big risk of contamination by macroparticles. And that's a field which becomes more and more interesting, because more and more products need contamination control. For instance, when you produce a battery can be killed by a particle largely equal 100 micrometers. And so there are many more examples in automotive industry, in medical devices, where we see that we need to be able to control macroparticles. And I'll try to explain a little bit how we can approach this. And important is to have a look at particle deposition. At Brokerhuis Applied Data Intelligence, we try to provide instruments which you can use to improve your control of your product quality by controlling surface cleanliness and particle deposition. I want to first talk about surface contamination and potential contamination sources, and then the mechanisms which act during contamination. The likelihood of particle contamination can be expressed in terms of particle deposition rate. And when you know the functionality of your product, you can set cleanliness requirements which are important when you want to establish control. Establish your control by setting up a facility, but also a set of operational procedures, so that all processes can be executed by people. After establishing control, we can demonstrate it by monitoring various important parameters. And for that, I'll just show you a few measurement instruments. So surface contamination can harm functionality of many types of products. Particles can block critical optical information. It can harm electronic interconnection by creating shortcuts or open connections. It can disturb the geometry, for instance, of an engine or a gearbox. It can also, when you look at the inkjet printhead, which I've been working on for more than 15 years, it can block channels and nozzles. It can disturb also semiconductor properties. And when looking at vacuum, even particles can cause unwanted outgassing. Particles can also carry microorganisms, which is very important in many industries, in food, in pharmaceuticals, in healthcare. And most microorganisms are carried by macroparticles. So it's very important also to learn about how to deal with macroparticles. And by that, you can also control microbiological contamination. And the causes of microbial contamination can be illness, disability, and could even lead to death. Well, the sources of contamination are, first of all, personnel. People are the largest source of particles and microorganisms in a clean room. The second group are all incoming goods. If the goods are not properly cleaned and the process steps of transferring goods into the clean room, you often see that as a source of contamination. Another group which is often forgotten are all the surfaces inside the clean room. All surfaces act as a source of particle contamination, and especially when you don't clean very frequent, the number of particles on surfaces are increasing, and 1 out of 10,000 particles can re-enter into the air due to mechanical motions like walking over a floor, or turbulent airflows, or vibration caused by equipment. And then a next group is equipment. The moving parts of process equipment, of tools, can generate particles which can be partly floating and can be removed by airflow, but there can also be a number of larger particles which can deposit onto surfaces. So when we talk about a particle load from a source, it's easy to look at the number of particles larger than a specific size, and you multiply it by this particle size. This load can also be used to determine a surface cleanliness, and it can also be used as a potential contamination load. However, when we use a light scattering airborne particle counter, you look at the equivalent diameter of a particle, which is not the real size. But if you look under a microscope at a particle, you see the silhouette of a particle. Then mostly we take the smallest diameter of the circle which you can draw around this silhouette of a particle, and I give that as a capital D. And then we can express the contamination load as the number of particles largely equal particle size D times particle size D. Particles can carry microorganisms, and the larger the particle, the more likely it will carry microorganisms. In fact, the average size of microbe-carrying particles, when we look at the outer size of a particle, is somewhere between 20 and 25 micrometers. And there is a difference in different classes of clean rooms, but on average, the particles larger than 20 micrometers, half of those particles can carry microorganisms that will cause a colony forming unit. So that means that when looking at macroparticles, when you can control the contamination by macroparticles, you also can control the contamination by microorganisms. So if you manage to reduce the particle deposition, you also reduce the deposition of microorganisms. The contamination mechanism of a critical product service is by deposition from the air and by contact transfer. When a tool touches a critical surface of a product, particles from one surface can be transferred to the other one. But one should also realize that also a tool which is exposed to the environment will also get contaminated by particle deposition. So in the end, particle deposition is the major key. And particle deposition is a combination of sedimentation following Stokes' law and turbulent impaction. So when looking at non-unidirectional clean rooms, and you look at the different particle sizes, then you can see how good is the ventilation system in such a clean room. And I've been looking just the other way around. When we look at particles largely equal half a micrometer, somewhere between 1/10 or 1% of the particles will deposit. So more than 99% of the particles will be removed by airflow. When we look at particles largely equal 5 micrometers, 5 to 15% of these particles can deposit on surfaces. When we look one step further to particles, let's say largely equal 30 micrometers, already more than 50% up to 90% can deposit onto surfaces. And when we look one step further to particles larger than 50 micrometers, these are still particles which are invisible for the naked eye. 80 to 95% of those particles will deposit onto surfaces. So if you are dealing with a vulnerable product and people are moving around, you have large particle sources and people emit particles from all sizes, from particles smaller than 1 micrometer to particles up to larger than 100 micrometers. The number of particles emitted by people is reciprocal proportional to the particle size. Well, if you have information about this particle deposition rate, then you can also estimate what is the likelihood of product contamination. You need to know what is the critical particle size for your product. Say this is 20 micrometers. Then you need to know the particle deposition rate for particles largely equal 20 micrometers, and you multiply it by the surface area. And especially in many new products, we are dealing with large surface areas. And that means that the likelihood of contamination will increase. The other factor is time of exposure. The longer a product is exposed to the environment, the larger the likelihood of surface contamination. So I explained already that the amount of contamination expressed as the number of particles times the size is some kind of contamination load. And when you divide this by the area which you're observing, let's say the critical area of your product, then you can express this as a target surface cleanliness level. So when you know your target surface cleanliness level of your product, which you can find by doing a risk assessment. A risk assessment you can use to find your critical particle size, to find your critical surface area. You can find your critical location where the product is exposed to the environment, and you can determine the time of exposure. If you have these ingredients and you also know the cleanliness of your product, let's say just after cleaning, then the difference between initial surface cleanliness and final surface cleanliness, that gives you your contamination latitude. And if you know this contamination latitude, you can calculate what amount of particle deposition rate you can allow, and that that parameter you can use to determine the air cleanliness you need when you want to set up you want to establish control. Well, I was talking about particle deposition rate for as a number of particles larger equal d micrometers per square meter per hour, but you can also make it independent of particle size by multiplying this particle deposition rate with its particle size and divide it by 10, and then you express it as a kind of particle deposition rate level, expressed then in the number of particles larger equal 10 micrometers. And in the new ISO standard on particle deposition rate application, there is a table that shows you the different particle deposition rate levels from 1 to up to 1 million. And you can see that that let's have a look, for instance, at particle deposition rate of 1000. That means not more than 1000 particles large equal 10 micrometers per square meter per hour. And when you want to know the situation for 50 micrometers, you divide the number by 5, and then you have the level you can expect for particles larger equal 50 micrometers. So that's the way you can use this table. So in a clean room, the ventilation system is used to dilute the particle concentration in the air to achieve a certain air cleanliness, but you also use your ventilation system to remove these particles from the clean room. And at a critical location, there is a relation between the air cleanliness for particles large equal 5 micrometers, so the number of microparticles per cubic meter, and the particle deposition rate for particles larger equal 5 micrometers. And I've given this relation in the shape of a graph. And in the same graph, I have also put a relation between the number of particles in air and the associated clean room classes. So you can see that if you have a particle deposition rate level of 10,000, then for particles larger equal 5 micrometer, you can then calculate the acceptable airborne contamination concentration of particles large equal 5 micrometers, which is 500. So this means that if you have a critical location within the ISO 6 environment, 6.5, you would be okay. It should be better than that. It's a bit too small to look at. So, but this relation which I've just shown you is only valid as long as airflow can remove particles. And I showed you already that particles larger than 50 micrometers will not be removed by airflow very effectively. So the contamination by these larger particles you have to solve by having good operational procedures. First, try to limit the introduction with good entrance procedures, right choice of garment use, and secondly, a very good cleaning program. Cleaning of all clean room surfaces, but also cleaning around the critical area, process equipment, and tools. So with these ingredients, you can set up a facility, and this facility should provide the right air cleanliness, but should also provide the means which you need to execute your procedures. This approach is described in the new ISO 14644, and at the moment also ISO 14644 on clean room operation is also being revised, and then we have all the ingredients for setting up a good operational procedures. Once the control is established, we start training people who are going to work there, people who are going to maintain the facility, and we verify if the facility works as planned. And after that, we can go into operation, and we can demonstrate control by monitoring air cleanliness, monitoring particle deposition rate, and monitoring surface cleanliness. Especially monitoring of surface cleanliness is not done very often because there is no good equipment yet. But if you have a small sensor where you can easily take, let's say, 20 samples from the floor, from your workbenches, and so on, then you get a lot of new information because you can see the effectiveness of your cleaning program. You can see how fast the surfaces are contaminated, etc. You can show any trending. And when necessary, you can improve control. So the measurement methods, which I've just described, are in the cleanliness standards, but also in ISO 14644 part 3. For surface cleanliness, we have to look at part 9. And when we want to measure surface cleanliness, you can do that direct by looking through a microscope or a kind of microscopical device onto a surface, and then count the particles largely equal a certain size over a certain measurement area. You can also do that indirect by removing particles from the surface and counting them, and that can be done by air or by a liquid or by a tacky surface. Here in this slide, I have a number of pictures. First of all, I have two new service monitors. One that is the PartSense 4.0. It can count particles larger than 5 micrometers and a measurement area of 2.7 square centimeters. The other one is the Summon. It counts particles larger than 20 micrometers on a measurement area of 10 square centimeters. So that means that both these instruments have a lower limit of surface cleanliness of 20,000 per square meter, which is about ISO SCP 4.3. Then in the line below, first two pictures are examples of removing particles from the surface with airflow, and then counting the surface in the particles which are removed with a light scattering airborne particle counter. Secondly, as an example of counting particles which are removed by a liquid, you can either use a liquid particle counter or you filter the liquid, and then you can count particles on a filter. And then the last method is a tacky rubber surface which you can use to collect particles from a surface. And then there is an instrument, the fast micron, with which you can count particles largely equal 1 micrometer. That way you are able to measure particles on a surface, which you can use on a product surface, on tools, workbenches, etc. Well, the other group of measurements is the real-time particle deposition monitoring. In fact, traditionally, we measure particle deposition by putting a witness plate, knowing its initial cleanliness, and leaving it for a few hours, and then collecting it again and measuring surface cleanliness. But it is also possible to have instruments with a test surface which can measure the surface cleanliness every few minutes, and by that you can see the change of surface cleanliness, and that gives you information on the particle deposition rate. So measurement principles can be holographic, or can be optical, or it can be done by scattering, or by means of mass. When you use a quartz crystal monitor, you can look at the change of mass, and it can be very sensitive. Here I've shown you a number of instruments where you can use to measure particle deposition rate. On top you see the holographic instruments, the Upmon and the Upmon 2, which has been launched this year. And below left, you see two instruments which use a glass witness plate to collect particles and to make within a very short time a picture. Then we have the cubic instrument, the CLEPART, which measures every 7 minutes the number of particles largely equal 5 micrometers. And in the blue instrument is in fact a kind of CCD, and you look at the shadow of particles. The upper right instrument, the Upmon 2, communicates with the internet, so there's no computer necessary. It sends the data to the internet, and the internet can be accessed by a tablet or a laptop, and by anybody who has a clearance can look at the data and take the selection of the information which is important. So a facility manager wants to have different information than, for instance, a quality manager. Here's an example of the real-time graph. And you can also look at the cumulative distribution. And this type of measurements are used in different type of industries, in life sciences, automotive, in electronics, aerospace, medical devices, batteries, displays, print heads, and I think automotive I also mentioned, yeah. So next to particle deposition monitoring, you could also have an instrument which looks at the surface cleanliness at different surfaces inside a clean room. And when you take a measurement just after cleaning and then a few hours later again, that way you can also have an idea of the particle deposition rate inside your clean room. And that way you can extend the locations where you can test the change of surface cleanliness. And this instrument you can also calculate automatically cleaning efficiency and particle deposition rate. So this was my presentation. I think that in clean rooms where people are working, the particle deposition rate is the key parameter that connects air cleanliness with product cleanliness, and it can help you, it can guide you in making the right decision on ventilation, discipline, and cleaning. And real-time information can also give you an idea of what are moments of high particle emissions, so that you can also take care of particular sources inside your clean room. That was my presentation.
Okay, thank you, Koos, for a very interesting presentation. The third in line. So this is the end of the presentation part of this webinar, which is organized because of the 50th anniversary of the ISCC'22. As chairman of the technical committee of the ISCC'22, I'm really thankful for the VCCN organizing this and having such good presentations, such perfect speakers here today. In the meantime, I just remind you that it's possible to post questions in the chat if you have any, because we could try to answer questions that pop up with you. Giving you the opportunity to do so, I'd like to point out to you that there will be a couple of these webinars over the year, and the next webinar that is planned for is the third one on the 8th of June this year. So please mind the agenda, and maybe we can welcome you again on the 8th of June. And I also like to point out that there's a very interesting live as well as virtual symposium coming up on the 11th till the 13th of October this year in Antalya in Turkey, where we as ISCC' celebrate that we have the 50-year anniversary and also have an interesting symposium. And it's also possible to submit abstracts. So if you have very interesting topics that you would like to share, I'd also invite you to go there and go to the website and check out whether you are able to submit as an abstract and maybe have a presentation there. I'm looking for the chat and I don't see that much questions. Still, I have a question, so maybe I can ask Eric and also Christopher also on the podium again. Just because I have a question. What I was listening to in your presentation, Eric and Christopher, was that we were focusing on smaller and smaller, while on the other hand, Koos was talking about larger and larger. So I'd like where we are now. Is this also something in view of your perspective?
Yeah, actually, it's a very nice program that we have here, because I think Koos indeed mentioned very clearly that we have to cover the full spectrum. And of course, when we look at, let's say, our presentation, we try to look, let's say, in the future. Of course, there things become smaller, and even particles that we cannot define as particle almost will become more and more important. But definitely, I think we agree that also larger particles, we should not, let's say that we can easily control them and that we have them in control. And it brings me also back to almost 20 years ago, that when I also started at VCN, I remember that actually also Koos, I think, indicated that particles are basically something which are very much driven by humans and driven by mechanics. And it's interesting to see that we are still not in control there. And so therefore, I think it's very good to again also look at an integral approach, and that we should cover the full spectrum. And that makes also, I think, also the contamination control in let's say almost a science sector to think, and I think that is also good. But maybe Chris, you would like
No,
to
I
add?
mean, I just like to add that the issue is with the size of particles, as you say, people are the source of largely the source of these, and that this is where people hit equipment, and one of these issues is people are needed to understand and control the science, but increasingly people are removed from the process to deal with this form of contamination. So I think the technology is likely to keep removing people, partly for the very reasons you've been discussing.
Yes, but people are very flexible. They can observe what's happening. They can make decisions, and it's very difficult to replace human action by robots. I've also been working on that for many years, and you can only do that when you have simple operations and they are repeated all the time. But otherwise, you still need people, and you need to find ways to separate a person from a process, uh, but still keeping control by the person.
In the meantime, I see there's one question coming in. It's by Olaf Teulings. Do airborne particles deposit the product on the product or follow the airstream? That's the question. So maybe, Koos, you can give a short answer.
Well, in fact, particles follow the airstream, but in a clean room, these pockets of air are moving through the clean room. But inside the pocket, you have gravitation working on these particles, and the particles are moving downwards by gravity. And then it depends on the particle size, how much time it needs to deposit and onto a surface when a pocket of air passes a surface. If this time is short, then the likelihood of deposition decreases, and then the particles which are deposited, also the particle size will increase. And this is related to the air change rate in a clean room. And you can, of course, reduce particle deposition by increasing the air change rate, but it takes you a lot of energy. And by trying to find measures to keep surfaces clean, to limit the introduction of particle size and monitor this particle deposition monitor, you can improve this control, and by that reduce the amount of energy you need to remove these particles. And in the end, particles larger than 50 micrometers are very hard to deal with airflow.
Okay, thank you. I see another question coming in. What is the role of computational fluid dynamics in understanding particle behavior in air and likelihood of deposition?
I don't have a good answer for that, because the larger a particle, the more difficult it is to show the behavior of the particles with respect to the airflow. And CFD is already difficult for airflows, especially in and around equipment and tools, because you get a lot of turbulences. So then you need a very detailed approach, and CFD is good for a more holistic approach, but not for the details. And especially when you look at large particles, it will be difficult. But of course, you can make experiments and compare results. I've done tests in the past where we did CFD, and we made also a test setup and look at the behavior of particles in different airflows. And you get information, the information of the two different tools together give you an understanding what's going on. But you cannot exactly predict what's going to happen.
Okay.
Maybe I can add to that, because I think the word understanding is very important here. It is not, let's say, an absolute measurement or an absolute visualization of it, but it gives you a very good understanding of what might happen or can happen. And basically, then you can translate that into the correct countermeasures. So especially when you do designing for clean rooms and also in operation, it's a very useful tool. But of course, it has its limitation. It's not the real world.
In the meantime, there are two other questions coming in. First is about the new revision of the -4 of the ISO 14644. When is it expected, and what are the major changes? Well, that's a topic in itself, basically. But in general terms speaking, the DIS has been approved, and we have been working last week on the FDIS version, which will be issued soon to ISO. Then it will be processed, and then there will be a formal ballot. So end of the year, we should know whether we are going to get this version, this FDIS approved, and we expect as a working group that it will be accepted. So end of this year, early next year, it will be formally issued, probably. What is the difference between the old one and the new one? Well, there's a lot of stuff that has been reorganized, but a very important one is that we have to look at all the contamination substances that are around, not only particles in air, but also chemicals, viables, nanoparticles, as well as the contamination on surface instead of only in the air. And we look at source strengths as good as possible, which is totally different approach, more scientific approach than just having a clean room designed by a number of air changes for a certain class, which is, yeah. So that means that you have to consider what is the cleanliness you really need, and you have to consider what is the contamination source that you expect, or what are the sources you expect, and then you can develop your design. That's in brief. There's also a question on the Annex 1 and GMP applied life science, and how does particle deposition coincide with that? Also looking at recently, last year, also issued -17 of ISO 14644, which is about particle deposition rate applications. And well, you can quite simply say something about that. Maybe, I don't know whether you have a view on that.
Yeah, when you look at air cleanliness, unfortunately, when looking at particles, the Annex 1 is only limited to particles large equal 5 micrometers, while they should have a look at particles larger than 20 or 25 micrometers, which will be more useful. But looking at colony forming units in air, on surfaces, and settling, sedimentation, that provides the same type of information. The only problem is you have to wait some time before you have the results. And therefore, I like to promote particle deposition and monitoring also for life science clean rooms. But it will take some time. We probably have to build up more experience, because the introduction of the particle deposition rate monitoring is in ISO 14644 part 17, which is published last year. So we still need some time, need to build up experience, but in the future I think it will become more important.
Yeah. I see the question also developing a little bit with respect to GMP applied to life sciences, but also to medical device manufacturing, because the question is, do we expect that the standard of particle deposition rate would be relevant in that medical device manufacturing world, especially when you look at a lot of medical devices are generally thermally sterilized. Is there any opinion that you have on that?
Well, going back to the theme of what we've been discussing, I suppose it's where the medical device begins to overlap with other technologies. So, for example, if you have an implanted hearing aid, which exist, then you need to be able to sterilize it without destroying some of the microelectronics that will be within it. So you really need to combine sterilization with protecting the electronics.
So there will be some step of aseptic processing,
Yes.
probably
Yeah.
somewhere at the end of the process of configuring the product. And there I think that particle deposition is a very useful tool to control the bioburden or particle burden that might happen, because that's something that you can do. There's, as explained, the -17 will show quite well how you can deal with that information and what you could do. Recently we had within the VCCN, we had also a meeting on particle deposition, an event, and there was also introduction by Line Blikken Olsen from Denmark, and she showed that it's also relevant within the pharmaceutical world when you want to control whether, for instance, your vials have any particulate contamination, which is not necessarily found that easily. So there, sedimentation, deposition can be a useful tool to study that process. And looking at that -17, it's also very clear that it states a couple of strategies, and one of those strategies is keep the people out, keep as much as possible other equipment out, and that's exactly what you see when you talk about wraps or even more isolated technology, which is very profoundly found in the new Annex 1. Another question I have to read for Eric, and new technology trends related to automation and robotics. Do robots add contamination, and how do you intervene to make any adjustment inside, say, an isolator or wraps?
Of course, let's say it's a process that goes back and forth. Of course, when you look at especially high-tech industry, there's a lot of experience with creating robots, so the robot in itself, the mechanics. But of course, when you put it, let's say, into an environment that also has strict particle control, then you enter, of course, a new world almost. But what I do see, especially when you look at the semiconductor industry, their robotics is, of course, part of the machine itself. So there is a lot of experience with designing the robotics with the correct materials, etc., and all that kind of things. How to make sure that this will not introduce additional particles or any other type of contamination. And I think what I'm working both in the semiconductor industry, also in the life science, and what I always observe that there are still two different worlds almost. So my message or my question would also be, please come together and learn from each other. Although maybe the application seems completely different, there are a lot of things we can learn. And just to give you also maybe a final example on that, when you look at ASML, basically they developed a new type of technology science, and also what Freek explained. So they entered the vacuum world, which is completely different from what they used to do. But by getting the right people together, then you are able to develop, let's say, it in a certain way, and you can make steps much more efficient and also much more practical as well. And of course, you can also introduce them much faster in your process. So that would be my, let's say, my conclusion. Chris, you have
No,
something to add?
I don't have much to add other than, and obviously these clean rooms are full of pieces of equipment. They're full of tools, and in a way, a robot is another tool. So, and I mean, equipment does produce contamination, which needs shielding and containment. So, I wouldn't say that it's novel. I'd say that it's a continuation of manufacturing technology in the first place.
Mm-hmm. Okay, thank you very much for your answers, your presentations, the good discussion. I think that this final question and the answer underlines, say, the relevance of having organizations like the ISCC', the VCCN, and all the other associated societies worldwide, discussing from various perspectives and disciplines, and bringing all those knowledge and efforts together. So I'd really invite you to make sure that you follow ISCC' and maybe look for a local society wherever you are in the world. There are quite a number of them. You can find them on the website, which is ISCC.net. And once again, I remind you of the symposium in October in Antalya. And for now, I'd really like to thank you all for attending this webinar, and hope to see you at least again on the 8th of June. So thank you very much, and goodbye.